All right, hello everyone. How's everyone doing? Wonderful. Just so I can show everyone, who here is from the UK? Who here is from outside the UK? All right. If we're coming from Europe? North America? Asia? Okay, so most, it seems like a large European, mainland Europe. Is it mainland or continental Europe, I should say? Somewhere from the continent. Okay, cool. All right. So everyone here is for machine learning in R, correct? Not Econ 305? All right. Just always make sure you never want to be in the wrong room. I don't want to be in the wrong room as much as you probably don't want to be in the wrong room. So to get started, I created a GitHub repo that I will continuously push to throughout the class and has some stuff that will help you get started if it'll make your life easier. So you give me a second, I will pull that up here, and we can all get started together. All right, I'll pull this up on the screen, and I will do my best to adjust my font as we go forward.
What, do you want us to clone it?
You have an option. You can clone, or I've made it even easier for you. Who's familiar with Git? Show of hands. Who is not familiar with Git? It's OK. You can admit if you're not good with Git. It's OK. It's a hard thing to know. But if you come to this URL, which is really hard to see on my screen, I will read it out loud to you. It's github.com. Everyone knows that part. /Jared Lander, JARED LANDER, /ODSC London 2018. Now, if you're good with Git, you can just go ahead and clone the repo, and you're in a good position. If you're not familiar with Git, the instructions here are designed with you in mind. These are like a lot of packages. We'll probably only use some of them, but I put them all up there. If you would like to install these packages, go ahead and install them. You will need at least a few of them. Actually, everyone should go ahead and install these packages. Actually, well, let me rephrase that. At a bare minimum, right now, you need to install this package right here called UseThis. Everyone sees that right there that I have highlighted? Show of hands, do you know how to install a package in R, just to make sure? Thumbs up, thumbs down. Thumbs up if you know, thumbs down if you don't know. So everyone here has some proficiency in R. If you don't know, I'll go over that in a second. And again, what I'm telling you right now is only for people who aren't comfortable in Git. If you're comfortable in Git, just go ahead and clone the repo. If you're not comfortable in Git, after you install that one package, you can run this line of code, which you can copy and paste from the repo. What this will do, it will actually download this whole repo to your computer and create an RStudio project for you, so you don't need to know any Git to get started. You don't even need Git on your computer to get started. Not everyone understands Git. And again, if you don't know Git, don't worry. You should learn it. You absolutely should. But it's a steep learning curve, and a lot of people don't know it. All this will do is set us up with an environment to get started. OK, so it's nice. It's handy. It just makes sure it will make your life a little bit easier.
Sorry, can you repeat the address there?
For the GitHub URL?
Yeah.
So it's github.com/Jared Lander /ODSC London 2018. I'll just give everyone another moment to make sure you got that. So did everyone successfully manage to get the repo down? Thumbs up if you have, thumbs down if you didn't. All right. Most of you in some form. If you're having trouble getting the repo, I will show you some lines of code on my screen in 1 second that will help you out. There we go. I'll have this up on my screen in a second to help you out. Whoa, that's really tiny font, isn't it? That's going to kill you. All right, I will change my font for everyone. I don't want people walking away with vision problems. All right, wow. All right, I'm going to close this and start again.
You know command plus.
I can, but I was trying to do that, but it wasn't working. So I'm going to, if something doesn't work, shut it down, open it up again.
With an error, this is not available for other versions 3.4.4.
So you have to install the use this package first. Did you try installing it?
Yeah.
That should be available for 3.4.4. If it's not, get 3.5. All right, let's try this again. All right, that font's a little big, but I think we're going to have to stick with this for now, OK? People in the back, can you see this well enough? If we make it any bigger, it will be impossible to see. So we got to go with this, I think. Wow, that is huge. I'll do my best to show you the console and this at the same time. All right, so before we get started, we only have two hour-and-a-half sessions today. We have the morning, hour and a half until lunch. Then we have another one after lunch. So I'm going to have to go a little bit quickly. I'm going to hope everyone can keep up. If you can't keep up, I'm going to post the code to GitHub periodically, and so you'll be able to get it there. If you get lost a little bit, don't worry. You'll be able to get the code. Just try to follow along. That's more important than getting every single line exactly. Also, as you run this, you are going to get errors. There's just no way about not getting errors. If you get an error, don't stop everything. Don't raise your hand. I have an error. Read your error message. They actually tell you what's wrong. If you're new to R, they might seem cryptic. But I promise you, if you read them, you will get good at them. If you can't understand the error message, read the end of the error message. The end is where all the good stuff is. That's where they really tell you where it is. Now, I've gotten very good at reading error messages because I've gotten a lot of errors over my lifetime. By getting errors and reading them, you learn how to deal with them. So you get an error, fight through it. All right? If you don't get any errors, by God, that's amazing. So today we are going to focus on supervised learning. When I say supervised learning, what does that mean to people? Shout it out.
Labeled data, unknown outcomes. Oh, known outcomes, I beg your pardon.
Known outcomes. Anyone have another definition?
The easy kind.
The easy kind. Easy is relative.
With a teacher is one I've heard. You
Oh, with a teacher,
the
yeah.
outcome, they call it with a teacher telling you you're wrong and then you try and minimize your loss and use a weight or whatever.
And hits you with a ruler every now and then, right?
There you go.
Yeah.
A teacher like that.
Oh man, I thought that was illegal. So basically you have X input data and Y outcome data. That's the whole idea of supervised learning as we're going to look at it today. So let's figure out exactly what we mean by that. Let me just pull something up here. All right, well, I don't have that, so let's come right here. So first thing I'm going to do is I'm going to open up a new file. And what I'm doing right now, no one needs to do, OK? This is just a little bit of exposition to explain what we're doing. We're just going to do a little bit of math. The whole idea of what we're going to focus on today is where y is a function of x. OK, that should show up there. Great. Everyone gets that? Y is a function of x. Y is your output data. X is your input data. Now, what this function is totally dependent on the methods we are going to learn. So today we are going to focus on penalized linear regression and boosted trees. Those cover 95% of what you want to do with, not just probably cover 98% of what you ever want to do with machine learning. right? You start with a linear model, you penalize it to make sure you're not overfitting, then you move on to a tree-based model. And that tree-based model could be a single tree, a random forest, a boosted tree, or a combination. But we're going to focus, all of our problems right now will be this idea here. Now let's talk about terminology. Let's talk about the x variable. Depending on the field you come from, these could be predictors, inputs, data, which I think is a stupid name, could be covariates, features, could be any other terms we have for the input?
Attributes.
Attributes.
Independent variable.
Independent variable. And I knew someone was going to say that, and I hate that term because that's when the y is also dependent variable. So A, they're a mouthful. Independent variable, dependent variable, they're easy to confuse. But worse off, the laws of probability say if x is independent of y, y is independent of x. So I take offense when x can be independent and y is dependent. It's a terrible terminology, so we're going to throw that out. Thank you for throwing it out there. And it could be any other number of names for the x's. Now what about the y variable, the outcome variable? I like calling it a response. There's lots of other terms. What do we got? Label, target, dependent variable, which we won't use, right?
Observations in the experimental world.
Observations, right? All these different terms. So let's disambiguate. I'm going to call it inputs and outputs, not to confuse anything. I think that's fair. Now it's funny, like when we learn XGBoost this afternoon, the x's are called data and the y's are called labels. First of all, it's all data. And second of all, they're calling it a label because they clearly were only thinking about classification when they built it. What about regression, continuous outputs, which is a lot of what you want to do? That's a label now. Input and output. This way we don't have to worry about it. So this y equals f of x. F can be any function of x. It's a function where you take in x values and you spit out a y value. That's all that is. Think about any mathematical function or any computer function that you need. OK? So for us, our first type of function is going to be a simple linear function. Should I pause and take a smile?
Oh, thank you.
Not sure if you want a candid or an action photo, whatever. I got to like run across the stage. Nope. All right. Cool. So our first function that we want to think about is simply going to be a linear function. This could take the form of y equals a plus bx. This is everyone's favorite equation from middle school, which I know is called something else here. Was it grade school or what, 5th grade, 6th grade, 7th grade?
It tends to be middle school.
Middle school. All right. We'll call it middle school here, as they call it in the States too. It is slope-intercept form. A is your intercept. That's where the line crosses the y-axis. And B is the slope. It's how steep the line is. Right? Everyone's seen this like back in the day in grammar, middle school, whatever school we want to call it. Right? So that's the first function. This is a function. This could actually be rewritten. I'll put another little equal sign in here. Equals f of x. Right? Y equals f of x. And this function happens to be a plus bx. That is a linear function. Now, what happens if you have multiple x's? Well, this can become a mouthful to write. Oh, wait, I'll pause for 1 second. Yeah. In that case, it was a screen, right? So we can rewrite this as y equals a plus b1 x1 plus b2 x2. I think I'm still typing correctly. I'll scroll up a little bit. That doesn't look right.
You've got an extra underscore.
Thank you. b2 x2 plus l dots plus bp xp, right? And of course, I messed up something there. I forgot a plus sign, right? Essentially, you can have multiple inputs, x1, x2, x3, x4, each with their own slope. Now let's talk about these b's, also called betas if you're doing this in a multivariate fashion a little bit. These are called, there's a slope. It's literally how steep a line is. But now instead of just having a line, you have a multidimensional hyperplane. What the hell is a hyperplane? Imagine a line. If you extend it in the next dimension, it becomes a plane. Then you extend it orthogonal to that, it becomes a multidimensional plane, and you can no longer see it in your head because humans are trapped in a 3D world, right? But essentially, it's a dividing line. You can think of these have multiple slopes as if you're climbing a mountain, and as you look around, it has different slopes in different directions. Well, that's multiple dimensions, and a mountain is 3 dimensions. You have a slope that way, and a slope that way. And it could change depending what direction you're facing. We call it a gradient. Now, these are b's, betas. As a statistician, I would call these coefficients. A lot of people now in the machine learning community call them weights. I really despise the term weights from the point of view that in statistics, weights tell you how important rows of data are. All of a sudden, we're taking an old terminology and reusing it. Now, there's a lot I can go off on about that, but we are sort of stuck with the words. Let's disambiguate. I will call them either slopes, coefficients, or weights. Everyone cool with that? Those 3 words to use interchangeably? I'll assume that's a good yes. All right. Now, of course, weight sort of does seem to make more sense from a layman's point of view, but from a statistics point of view, it means something totally different. Now, let's extend this to multiple dimensions. Well, we already extended it. Let's rewrite it in a more compact notation. I love writing it in the long form, but it can get laborious. So in matrix notation, we can rewrite it like that. Y equals beta x. In this case, we're talking about matrices. Show a thumbs up. Thumbs up if you're familiar with matrices. Thumbs down if you're not. Most of you are familiar. For those of you who are not familiar, don't worry. We're not going to have to do any matrix calculus. I promise you we won't do that. We won't even do any matrix algebra. All right? The whole goal here is you have these betas, and there's just a more compact form of the equation above. And believe it or not, if you were trying to derive this, say, for your linear regression class in grad school, it's actually much easier to do the math on the matrix form than it is on the regular form. Because in the regular form, you have p variables. You need to take p derivatives. You need to solve p equations. If you have the matrix form, you just need to remember how to do the derivative and equation once. So the whole goal here is that we have our input data x. We have our output data y. And we want to find the values for the betas, the b's, that best associate x to y. This is old school linear regression. That's why I'm going a little bit fast. So I assume most of you have taken some form of linear regression. So the whole idea is to solve for beta. That's it. It's actually technically an optimization problem at this point, but it has a nice closed form solution. You could solve this with a pencil and paper. So our whole idea is to find betas that most closely approximate x to y. Does anyone know what that beta equals? In fact, it would be beta hat.
It's that formula I could look up on Google if I wanted.
You could look it up on Google. In fact, I tell my students at school, don't bother memorizing any equations except for this one. This one I find to be kind of helpful. So I'm not going to make you remember it, but it's x transpose x inverse x transpose y. That is the closed form solution for this problem, which you could figure out using matrix calculus, but we're not going to do that today. I have the equation memorized, or you can look it up on Google. All right? Our whole idea is to solve for this. Fortunately, R will do this for us all automatically. And if you want to get into real computation of things, because sometimes computation can be a consideration, x transpose x inverse, you never invert a matrix unless you have to. Sometimes you see some people, they will see the mathematical formula, and they go try to turn that into a computer program just as they would read it in math. But math doesn't always translate nicely to computation, and they will go ahead and invert this matrix. Problem is, this can be a very large matrix, and it can be hard to invert. So you would use pseudo-inversion. You might use a QR decomposition. You might use a Cholesky decomposition, or any other type of pseudo-inversion. Do we need to worry about that at a base level, at a high level? No, not really. We'll let the computer do it all for us. Everyone cool? All right. So let's go ahead and start doing some programming. I opened up a new text editor in R. I encourage everyone to do the same. If you're in RStudio, Control-Shift-N. If you are on a fruit-based product, it is Command-Shift-N. OK. Does everyone understand the idea that a regression is just a best fit line? Everyone gets that? I don't need to go over that? Cool. All right. So we are going to need at least 3 packages to do this. If you don't have these packages installed, install them. The first package is glmnet. The second package is useful. And the third package is coefplot. If you don't have these packages, if you get an error message when you try running any of these lines of code, install the package.
Can I ask a dumb question? It looks like you're typing in our source file, but you're doing something magic when you hit return, so it gets executed.
So yeah, so if you're not familiar with RStudio, I'm not quite hitting return. I'm hitting control return. And if you're in the text editor, you hit control return, the code gets sent to the console and executed. There are a lot of shortcuts in RStudio that will make your life a lot better. Holy crap. Then you're going to want to do this. I don't know what the shortcut is on a Mac, but on a PC, Alt-Shift-K brings up a list of keyboard shortcuts. And my favorite keyboard shortcut this lists is Alt-Shift-K to bring up the keyboard shortcuts. You have to know how to get there. It's like the forest in Zelda. Pardon me? Oh, Alt-Shift-K? Nice. Because on Mac, people, on the newer Macs, the Alt key no longer says Alt, it only says Option. Yeah, why did they have to stop printing Alt on there? Did that cost them that much? Okay. So, on the GitHub page, we downloaded some data. Now, we might have skipped over it to speed things up. What I'm going to do is I'm going to put up a little snippet for you to download a little bit of data, and then I'll put it on GitHub so people can just copy and paste because the link is a little iffy. Where is this? Actually, if everyone cloned the repo, if you can come to the folder that says prep, and there's a file called downloaddata.r. If you click that, we only need, let's first run these two lines of code here, line 1 and line 2. This is just doing some magic to make use of working directories a little bit better. In order to use line 1, you will need to install another package, rproj-root. Can people read my screen well enough? It's not the size at this point, right? It's the colors.
I think that the blue's a bit unfortunate. I mean, I know it's just comments, but
You know what we can do?
you just make it white on black.
Can you switch off the lights above the stage? That would help you.
Are we able to turn off these lights?
That would help you.
Oh,
Let me ask you. I think that it's a video recording, which is why they need the lights.
Yeah, but it will help with the video recording.
It's wrong, it's just a white on black.
how's that? Is that better, folks?
Yeah.
All right. It's not as cool looking, but it's readable. OK. So did you successfully run these lines of code without an error? Yeah? Nice. All right. So then let's just go download a few files we are going to need. If you come to line, let me do this. If you come to line 64, where it says Manhattan test.rds, and highlight that, Manhattan train.rds, and Manhattan validate.rds, and see if you're able to download this stuff. There might be an internet issue. Are people getting it? Thumbs up if it's downloading, thumbs down if it's not. Some are yes, some are no. I'll give you all another moment. And I'll make sure I can get onto it. I'm using the Ethernet and I can't download.
Oh, you wanted to use the
I'm going to try mine again as soon as I get a new internet connection. As we wait patiently. Anyone see any good movies lately? Do you want to talk about Star Trek? Have a fight? Not Star Trek, Star Wars. We can start a fight. Who liked it, who didn't? OK. So I have a new data set. they're all going to be now in our data folder. Oh, thank you so much. Does that work for everybody? Does it still work for the film crew? I'll take that as a yes. Yeah? All right, cool. So now, if we look in our data folder, we should magically have 3 files. Correct? People are good? Isn't that awesome the way it just works? You never need to go to your browser. I gave a talk. You should check out my website, jaredlander.com/talks. I gave a talk about how to do everything you need to on a computer without leaving R. I'm talking about downloading files, zipping files, sending emails, doing everything you need. It's pretty amazing. So now that we have our data, let's read them into R. OK? So we are going to say land_train gets read RDS data/Manhattan_train.rds. We can then view land_train. So if you're not familiar, RDS is a special binary file format for R that stores a single R object on a file on disk, and then it can be read into R very quickly since it's a binary. Nice, quick. It can be compressed at, I think, 9 or 10 different levels of compression. So you can really pack this in a lot. Of course, the more you compress it, the less disk space it takes up, but the slower it is to read and write. You have trade-offs everywhere. This data is about land value in New York City. Now, I have data for the rest of New York City, for Brooklyn, Queens, etc. But this data set we have today is just for Manhattan. There are roughly 32,000 rows in this data set, because there are about, I believe, 40,000 individual pieces of land available in Manhattan. Not technically available. Most of them are not available, actually, but the way they've been divvied up. And this data set has a lot of information. The first variable we will think about is total value. That is how much the land is worth. You can imagine that's important. And I believe in London, you're just as obsessed with rent prices as we are in New York City, right? Now, this isn't for rent. This is to purchase. And it's not for the building. It's for the land itself. I believe it's sort of similar here. In New York, the land can be sold separately from the building, and they have 2 different values. Now, of course, the value of the building will probably affect the value of the land, but they are separate things. And we have other information, some of which we'll care about, some of which we won't. Fire service. What type of fire service do you have? There's hook, ladder, and engine. There are some older terms. They still sort of apply, but let's not worry. We have zoning districts. I'm not sure how it is in London and in the rest of Europe. Am I still allowed to say the rest of Europe, or is that too soon? Yeah. Sorry, had to. When I come here, people make fun of me for Trump, so I'm like, Brexit. Yeah, if we're gonna have transatlantic making fun of each other, it's gonna go both ways. So we have zoning districts. Do you have zoning districts here? Like you could build a commercial building, you could build a residential building. Are there like rules?
We have planning regulations, yeah.
All right, plenty of regulations, good. So in New York City, at least, there could be 4 overlapping zoning districts your piece of land can have. And you can see here there's commercial, there could be missing, there could be industrial, there could be warehouses, all sorts of different types. Let's not worry about too much. We also have a variable called class, which seems kind of similar. It could be retail, could be public, could be office, could be residential. Then land use also seems similar. Mixed residential and commercial, public facilities, commercial and office. It seems like these 6 variables are going to be highly correlated with each other, right? Yeah. And that usually poses a problem when doing a linear regression. But we don't care about that. You'll see why. Easements, owner type, private, public, unknown, whatever. Here gets a very good example here. Lot area. Lot is the actual parcel of land. In the States, it's called a lot. I'm not sure that's a common term. So this is the square footage of the actual piece of land. Then you also have building area. Notice building area could be bigger than lot area. That could be for one of 2 reasons. The building has multiple stories, so each story could have the same, almost as much land as the lot. But also, a building can span multiple lots. The lots are chopped up into like small little pieces, or the parcels of land. But a building could span multiple of them because buildings are big these days. Then you have commercial area, and then residential area, and office area, and retail area. And if you were to add up all these different areas, they would equal building area or more. Because the way it divides them up, hey, you have an office area and retail area, and then you can get to factory and other area. And so those numbers are going to be highly correlated. We're going to get something called multicollinearity, which is a problem in traditional linear regression. Let's continue. You have number of buildings, number of floors, and yes, 5.5 floors. How can you have 5.5 floors? There's two possible answers I could think of.
It happens.
Well, it happens. How does it happen?
Is that movie?
Like an
John
attic.
Malkovich?
What?
Like an attic, kind of.
It could be an attic, but there's not going to be a lot of attics in Manhattan.
Some kind of tax dodge?
Or somebody split a regular floor into two to sell it to two different people.
It could be split.
One below, the one above.
It could be split. It could not necessarily tax dodge, but a way of making your land more valuable, because a floor is defined as, I believe, 12 feet. But if you have 18-foot ceilings, and you have two of those, and you have 36 feet total, is that 3 stories or is it 2 stories? It's divided by the number of feet. So now your land, all of a sudden, even though you only have 2 floors, you have a 3-story building. And you can also have a mezzanine. So there's a few different ways you can get half of a floor. You have the frontage of the building, the number of units in a building, the different type of units, the depth, all this different type of stuff here. And I'm not going to go through all of them. We'll care later on about a landmark or an historic district. Basically means if it's historic, you can't change anything on the outside of the building. I'm sure you have a lot of that here. And when it was built, roughly, at least down to the century, sometimes a decade, sometimes a year. For new buildings, we know the exact year. For older buildings, we know the century. I'm sure you have that problem here. All right. Any questions about the data? Our goal for this first session will be to model or explain the total value of the piece of land based on all these other input predictors. Now, we're not going to do all of them, but we're going to do a lot of them. So we need to define this relationship. And we define that in R using a formula. Thumbs up, thumbs down if you're used to the formula interface. OK. Well, I'll paste it on the screen. And you're all going to need to type this. Just kidding. I'm going to save it to GitHub. Don't worry. If I can find my mouse, I'll save it to GitHub. Are you folks familiar with the new terminal in RStudio? Invalid format. Oh, hold on. All right. So if you go to the GitHub page now, in the code folder, or if you cloned it, you could just git pull. In the code folder is a file called glmnet.r, glmnet.r. And then you can just copy and paste this. And if you fall behind, periodically throughout the day, I will save to the GitHub repo. This way you have it. So if I were you, I would not type this by hand, because you will get a typo probably. And by the way, 90% of your errors are going to be typos. Capitalization errors, comma issues, periods, parentheses, brackets. Those are going to cause 90% of your errors. So get this from the GitHub page, copy and paste into your browser, into RStudio. So what this is saying is we're going to take total value and model it, which is our output variable, and model it, explain it on all of these input variables. We're defining the linear relationship like this. Yeah?
Are some of the variables got factors?
Yes, they do. And we're going to deal with them magically. The question was, do some of the variables, are they factors? Yes, and I will explain factors in a moment if you're not familiar with them. It's a way of dealing with categorical qualitative variables. For so many years, and I still see this in many fields, people are obsessed with how do you deal with text data? You need to have one matrix for your numeric and a separate matrix for your categorical, and it's a whole mess. You have to encode them properly. It's all automatic in R. It's really beautiful. Everyone's copy and pasted this? All right. So this is a formula in R. And this is revolutionary. This won R Statistical Computing Award. It's really, really amazing. So again, what we're saying is output variable, tilde. That's a tilde. All of your input variables you care about. -1. We're doing -1 because we're about to build matrices. If we didn't do -1, we would get an intercept column, which is great. You need an intercept. But we don't need it because the function we're going to use will give us an intercept automatically. So don't worry about the intercept. If you're confused what intercept is, remember in our equation y equals a plus bx? It was the a term. It's where the line intersects with the y-axis. In machine learning, they might call it a bias. Problem is, in statistics, bias means a systematic bias that throws your analysis off. I'm not sure what they call that, right? Because there's the terms, we have terms for a reason, because they come from, hundreds of years of usage. And we're saving our whole formula to a variable, so we can reuse it a few times, because it will get a little messy. All right. I got a warning message, but don't worry, it's just a warning. Yeah, you can ignore most warnings. That might not be true in the rest of life, but here, in our case, we can ignore it. So if we were doing just a regular LM model, we could create a new object called value1 gets LM, pass it the formula, and the data equals land_train. And then we would get a linear model, which is kind of ugly. And if we did summary of value1, we would get many, many coefficients. In fact, let's do coefplot, and I'll explain this in a second, of value1, comma, sort equals magnitude. And it's kind of hard to see because of the zooming and everything. But this is a visual representation of our model. I'm going to take a moment to zoom in on this. Basically, each element on the screen is one of our variables, the coefficient, the weight, the multiplier for our variable. That's represented by the dot. And the wings represent the confidence intervals. Confidence intervals, well, the traditional definition is if you repeat the test 100 times, the true value will fall in this confidence interval 95 times, right? A less correct but easier to digest is that the true value of the confidence interval has a 95% chance of being in here. Not technically correct, but it's a little bit easier to digest. And we'll pretend we're Bayesians for a few minutes and assume that's correct. He asked me to talk about a p-value. So these are the confidence intervals, which are kind of related to a p-value, but p-values are evil, so we're not going to deal with them. Yeah. It's more, think of it as a credible region, but it's not because we're frequentists. Basically, what I'm trying to show here, and we will discuss let me explain the coefplot a little bit more. Right here, this is the y line, a 0 line. This means your x input variable, if it falls on this line, it had 0 effect on your outcome variable. The individual dot is our estimate for the weight for the coefficient. The confidence interval says what it's likely to be. And if you want to talk about statistical significance, if the confidence interval includes 0, that means the effect of that variable on the outcome is effectively 0. It's statistically not significant. Now, of course, we go into that territory. We start talking about p-values. Then we start p-hacking. Then we start doing dangerous science. P-values had a very strong role in statistics, and they were very valuable. But they're also arbitrarily designed by R.A. Fisher 100 years ago before he had a computer. So now that we have computers, we try to avoid p-values. I can go off on a rant on this, but just watch John Oliver. He did a whole episode about this, and I was like, oh my god, John Oliver's talking about p-values. It was great. And we can see here that this one, the confidence interval, is wholly outside of the 0. So therefore, that coefficient is statistically significant, if you believe in that stuff. This confidence interval is freaking huge, first of all, and it includes 0, so we could say that this estimate, this variable, is useless. It doesn't have any bearing on the y output.
What would you say about the second one from the bottom?
Yeah.
Its overlaps is 0. So it should not be significant. Now you could say, OK, well, take all the ones that are not significant, remove them from the model, and fit the model again. But then that changes things. And that's how you get into p-hacking. We're going to find a much better way to do that. Now, why do we have such incredibly large confidence intervals? And why do we have such large coefficients? It's what? 3 times 10 to the 6? That's because we are overfitting. How many variables did we put in here? It's like 90 roughly, I think, if I recall correctly. By the time you took all the variables and expanded the factors, yeah, without the factors, you're closer to correct. We have like 90 different effective variables here for 32,000 rows of data. Who's here to the curse of dimensionality? Thumbs up, thumbs down. Right? We have too much. So if you don't know the curse of dimensionality, it means too much data. Like, oh my God, you could have too much data? I thought more data is better. Not always. Especially when you just have wider data. And when you don't do any feature selection, you don't do any variable selection, you're going to get overfitting. And extremely large coefficients and extremely wide confidence intervals are indicative of overfitting. And there's many other terms for overfitting. You can say you have too much capacity in the model. I'm sure there's other terms. You call this multicollinearity. Lots of ways you can refer to this, but generally it's bad. And if you see you get a coefficient plot with extremely wide confidence intervals, it's bad. So traditionally, statisticians would deal with this through variable selection. They would go ahead and choose a bunch of different combinations of variables and see which ones work best. Bless you. Now you might say, OK, well, let's try every single combination of the variables and see which one does best. That becomes computationally intractable. If you only have 10 variables, getting every single combination is 2 to the 10 minus 1, which is roughly 1,023. That's if you have 10 variables. We now have 90 variables. What's 90 choose 2? Anyone want to do that math in their head really quickly? Don't worry about it. So you can see it's kind of a bad idea to do all combinations. Some statisticians are like, well, let's do stepwise. Let's look at p-values and remove and insert. I'm like, well, that's stepwise. You're talking about p-values again. Let's not do that. So we're going to use something called regularization, also known as shrinkage, also known as penalization. And yes, normally when I talk about shrinkage, I put up a picture of George Costanza coming out of the pool. For those of you who get that reference, that's awesome. For those of you who don't, you need to watch more Seinfeld. OK? Everyone needs to. Yeah.
So you said very wide confidence intervals. What is very?
Well,
Because here it depends on scale.
it completely depends on scale. Absolutely. So you need to know your data. If your data is in the tens and your confidence interval is in the millions, too big. Right? There's no one number I can tell you.
Yeah, but you can relate it to standard error or.
Yeah. So if all of them are, well, these are 2 standard error confidence intervals. There's always going to be 2 standard errors. So that you can't. It's sort of when you know it when you see it, right? I'm sure there's some mathematical definition for being too wide. But if all of your confidence intervals include 0, that's not a good sign. And generally in statistics, you prefer smaller coefficients to bigger coefficients, because that means a smaller effect, because bigger effects just often aren't realistic. A good rule of thumb when you're doing logistic regression is if your coefficients, your weights, are larger than the weight of smoking on mortality, they're too big. Because I think they found in the history of statistics, the effect of smoking on your likelihood to die is the biggest effect they've ever observed in logistic regression for a properly fit model. As a rule of thumb, not hard and fast.
But here I also cannot follow you. I mean, if you scale the dependent variable, then your coefficients become smaller.
Right, but they'll still, if you scale it, which our algorithm is about to do, they'll still be including, all of them will still include 0.
Yeah, for sure.
Right, and if they all include 0, that means none of them are useful, and that's the sign of overfitting. All right, so let's dive into our variable selection phase of the process. Let me just pull up something for you. I was going to type this out, but typing out this equation can be quite slow. So let me just pull up pre-typed. Give me a second. It's loading. There's only 40 variables, but when they become factors, they become more.
So cool.
Right?
It does it for you.
And I'll show you in a minute. He's talking about factors. I think a few people mentioned them. I'll show you in a few minutes about how to do factors. Let me just get to, oh yeah, the curse of dimensionality. See, there's a hypercube, but we don't have time for that. Oh yeah, see? So if you don't know this episode, this is one of the classic episodes of Seinfeld. Highly recommend watching this episode because it has real impact on statistics. All right, this is our equation. Our goal is to find a linear regression where the coefficients, the weights, have been shrunk towards 0. Bayesians will also call this shrinkage. And they would use a prior. We are not technically going to use a prior, though it can be interpreted that way. We're going to use this formula I'm showing you. You're trying to minimize this objective function, also known as a cost function. The cost is going to start with ordinary least squares. This part right here, if you were just to minimize this part, that would be linear regression, like the LM function in R, like everything you learned in basic statistics. That's this cost function. Y minus the predicted y squared, least squares. But we're minimizing that plus this penalty term with a lambda multiplier. Think of this as a, I believe, a Lagrangian constraint. Is it Lagrangian? Yeah. Lagrangian multiplier or Lagrangian constraint? I forget the terminology. Multiplier. We're doing constrained optimization. Okay? This penalty term right here can be broken down into two components, which we'll discuss. The L2 component, also known as ridge, also known as weight decay, and the L1 component, also known as lasso.
Why ridge? Where's the ridge?
He's asking, why is it called ridge? Where is the ridge? I used to have a good explanation for this, but I realized it wasn't. I'm going to show you a geometric representation. Maybe that will help out. Yeah. If you ask me, the lasso actually looks more like a ridge when it's throwing it off a cliff. But I'm sure they had a reason for it, and I'm not sure what the reason was. But the goal here is we are going to minimize the cost function, which is made up of some objective plus a penalty term. And our penalties are designed that if you have large coefficients, you get a large penalty. That's bad, and it'll try to minimize the whole objective while the focus on having smaller coefficients. Because the penalty for L2 is the sum of the squares of the coefficients. The penalty for L1 is the sum of the absolutes for the coefficients.
I would just go to the top of the ridge. Just wants to be 0.
Well, that's actually lasso, right?
Oh,
Right? The lasso looks more like a ridge.
yeah, exactly.
Yeah, I'm with you on that. I think they had a good reason for calling it ridge, but I don't remember what it is right now. I did read at one point there actually was a good reason, but it's gone. All right? So without getting too bogged down into the math, our goal is to solve this equation. All right? I believe, is this the only shapes I have here? Here's the shapes. You're right. Doesn't this look more like a ridge, the diamond point? But that's the lasso. And the smooth circle is the ridge. This is a geometric representation. Ooh, wow, we only have like 30 minutes. All right, I got to fly through this. Don't worry about the geometric representation. Let's just get back to coding. So our goal is to fit this model. In LM, all you needed to do was provide a formula and a data frame, and you fit your model. But glmnet doesn't do that. glmnet expects you to pre-build the X input matrix and the Y output matrix. So let's go ahead and do that in a nice, quick, easy way. We're going to create a new object called landx_train gets build.x. We are going to pass it a value formula, comma, data equals land_train, comma. On the next line, so it's more readable, I'll say contrast equals false and sparse equals true. What I'm doing is I'm building an X matrix, a design matrix, an input matrix. I'm giving it the formula, which is what we defined earlier, total value on all these predictor variables. I give it the data frame to pull these variables from. Contrast equals false. Very quickly, in traditional regression, if you have a factor variable with 5 levels, you will get 4 dummy variables back. Because if you do all 5 levels, you're guaranteed to get multicollinearity with the intercept. In glmnet penalized regression, we don't care about collinearity anymore. Bring it on. Include all the variables for better interpretation. So contrast equals false means if you have 5 levels in a factor or categorical variable, you get 5 dummy variables. And I'll show you the dummy variables in a second.
What library is built?
It's in the useful package, which you loaded at the very beginning. There are other ways to build this matrix, but this one just seems to be the nice, quickest, most concise way. Sparse equals true means build a sparse matrix. A sparse matrix is a better way of storing your data, takes up less space in memory, and computes faster. Likewise, we will do land y underscore train gets build.y value formula, comma, data equals land underscore train, and no other arguments. Now, the most 3 common mistakes I see people make at this point, they call build.x again when they meant to say build.y. They use the wrong name for the variable. They call it land x again. And they give extra arguments to build.y. So don't make those mistakes. Land y train gets build.y, value formula, data equals land train, no more arguments. There are no contrast arguments for build.y. There is no sparse argument for build.y. All right, that did not look pretty. Let's do this. No one has to do this. I'm just showing it to you. All right. Basically, here's the design matrix we just built. I'm going to expand this so it's easier for everyone to see. A lot going on here. Now, the reason it's printing this way is because my screen's not wide enough to show you everything. So deal with that. Basically, when we build this X matrix, numeric number data, let's say you had a column that was just a number, that column is just put into this matrix as a number. All right? Call it a numeric, call it a double, call it a float, whatever you want to call it. They're all going to be numerics here, all doubles here. Even integers will be treated like a numeric. But your categorical data, such as fire service, gets automatically turned into dummy variables or indicator variables or one-hot encoding. So you read it across. Was the fire service engine? No. Was the fire service ladder? Yes. Was the fire service squad? No. If we scroll down, all the different zoning districts, class. For class, there is asylum, automotive, condo, education, elevator, apartment, loft, industrial, hotel, health, government, probably on and on. Now, oh yeah, look at this. Look at all these different classes.
So the lm function does the very same thing?
Yes, it does. The question was, when I called lm, it automatically did this for me and turned a text column into one-hot encoding all automatically. It's magical. It's all thought for you. I can't wait to say it one time.
My variable is signed as an integer,
Mm-hmm.
and it's actually categorical.
So you're saying, let's say your data is encoded already as 1, 2, 3, 4
Grades. Let's say grades.
grades. Now, grades, however, you might want to consider that as a ordered factor. So let's not say grades. Let's say you encoded your data colors to be 1, 2, 3, 4, and they really represent red, green, blue, yellow. You should convert that, pre-process that into a different step, yeah. And we could do a whole other class in pre-processing, but we don't have time. All right. And so this is magical here, the way R treats categorical data. If the column is categorical and has different values, it will automatically be turned into different levels, or different indicator variables. And that was revolutionary. MATLAB didn't do this, I don't think, right? Python barely does it if it does it at all. SAS, I don't think, did it. It was a nightmare. If you did this in SQL, you'd be writing a case-when statement to do this, right? It'd be brutal. In Excel, oh my God, we're not even going to do this in Excel. But in R, all you need to do is put the variable on the right-hand side of the formula, and you're done. Look how magical this is. And we built out the X matrix manually for glmnet, but if you're using LM, it does it all automatically for you. It's amazing. That's why I'm so spoiled with this. Some people talking about Python. I'm like, OK, well, have fun building your design matrix. That's why when you do a Python workshop, they had the design matrix pre-built for you. Is Andreas here? We like to troll each other. Now, it's all a good sport. I put on the New York R conference, and Andreas, the guy who wrote Scikit-learn, spoke at the conference. Wes McKinney, the guy who wrote Pandas, spoke at the conference. So we can all get along. Even if the general communities don't get along, it's fine for individuals to get along. All right, back to what we're doing. Let's go ahead and fit our model. So the way we, I need to make this so you can see this again. That's not what I meant to do. All right. So let's go ahead and fit our model. We will call this model value2, gets, glmnet. Glmnet is the predominant way in R to fit this penalized regression. There are other ways to do it, but this was written by the people who discovered penalized regression, and it's incredibly fast because it's actually written in 73 lines of Fortran code. Anyone here program Fortran? 73 lines, is that a lot, is that a little?
It's nothing.
Nothing. And they did this in 73 frickin' lines. It's amazing what they do. These are Hasty, Tribshani, and Friedman. They are gods in the data science machine learning community. They are really, really good at what they do. So, glmnet. And it is pronounced glmnet, not glmnet. I used to call it glmnet because it seemed more natural, but I got lunch with Hasty, and he's like, yeah, it's called glmnet. I'm like, damn it. So let's do it with glmnet. The first argument to glmnet is your x input matrix. You do x equals land x underscore train. That's your x matrix that we just created. Then you need to supply a y variable. So we say y equals land y underscore train. And the y variable is just a matrix. It's just the matrix of y values. Right? Technically, it's a vector, but let's not get into the whole vector versus matrix thing. We don't have time for that. So theoretically, we could just accept the defaults. But just to make sure we're being very explicit, I will say family equals, in quotes, Gaussian. OK? We're doing a Gaussian regression because it's a standard linear regression. Does that make sense to everyone? Everyone knows Gauss? The bell curve is named after him. Pretty impressive dude. Very smart. So we run that, and we're done. It fit the model already. Now, when I say model, I actually mean models. What happened here is it fit a model for the data. But remember that lambda term? That's a tuning parameter. It's a hyperparameter. So what value of lambda did it use? Well, instead of doing 1, it did about 100 of them. So in that little bit of time, let's do it again for fun. It just fit 100 models. And the amazing thing about glmnet is that it can fit about 100 models, more even, in the same order of computations as fitting 1 model. And the way they designed the algorithm, they use something called a warm start. So fitting 100 models of 100 different lambdas is faster than fitting it with a single lambda. Kind of cool, right?
So mortals can't code this?
No. This was Jerry Friedman coding. He actually coded in Mortran, which generated Fortran. Yeah, mere mortals should not attempt this. And they have, and the things they do are not nearly as good.
I'd have some crappy loop.
Oh yeah, it'd be terrible. Yeah, no, not impinging on you, it's just hard to do. And they use upper and lower triangular matrices to make this happen, and they use coordinate descent. It's really amazing what they put together here. It's revolutionary how they did this. And I've seen other implementations of the elastic net. It's not nearly as nice or as user-friendly. If we try printing this out, and I encourage you not to, you get a whole bunch of stuff here. If we look at value 2 $beta, we get an insane matrix. So actually, let's try to view this. No one should do what I'm about to do. So what we get here is, along the rows, is each of the variables, is the coefficients for each of the variables. The columns are the different lambdas. So you can look at this as in this is one model, this is one model, this is one model, this is one model. And depending on the value of lambda, you'll either have a lot of zeros or a lot of non-zeros. If I were to scroll, you can see here, as we're getting to smaller lambdas, which we'll see in a little bit, we're getting more coefficients with values. And the whole idea here is, within a given lambda is one model. If the value is 0, the variable is not selected. It was excluded from the model. If the variable is 0, if the variable is not 0, I already said 0. If the variable is not 0, the variable is selected. And it has a value. It's allowed to stay in the model. That's the whole idea of what's going on here.
Once it's selected, the values don't.
They do change. They will change.
A bit, but not much.
Well, let's confirm. This is a table of numbers. It's hard to see what's happening, right? Does anyone like staring at a table of numbers?
Not in scientific notation.
No, definitely not in scientific notation. So what's better than looking at a table of numbers? Plotting.
Heat map.
Ooh, I never used a heat map. And we're not going to do coefplot yet. You could, but we're not going to do it yet. So there is a built-in function for glmnet. You could just say plot of value 2, comma, xvar equals lambda. Thank you. And I better make my screen bigger. When I do that, I get this plot. This is something that should be at the Tate Modern, right? And each line represents a different coefficient over its lifetime.
Looks like a supersonic wind tunnel.
It's kind of crazy. The x-axis represents lambda on the log scale. And you can see if lambda is small, all the coefficients are in the model. As lambda gets bigger, the coefficients shrink, they become smaller, and eventually some of them go to 0. As you move along, more go to 0. As you move along, they're all at 0. The top of the x-axis shows you, for a given value of lambda, how many are left in. So it says right here, for this value of lambda, there are 58 coefficients variables that were selected. For this value of lambda, there are 17 variables that were selected.
Is there some secret sauce that gives it start and end values of lambda before it does its parallel?
So the question is, what values of lambdas are we using? Well, you could specify your own, but you're better off letting it decide from the data. So the way they decide that is they do a dot product between y and each of the predictors, then take a lambda, that you take the max of the absolute of the dot products, and then that is your starting lambda, because that will involve all of them being 0, and then it does 100 of them down to, I forget what the minimum is, there's some ratio. I just computed this the other day because we built a new package for multi-level model lasso, but we'll leave that for another day.
But isn't there a danger of ending up inside a red blood cell when you should be off at Andromeda or something?
I don't think there's a danger. They've written papers about this, which I read 10 years ago, so it escaped me.
I mean, they're the smart guys.
Yeah, they built this thing pretty nicely. Now, each line represents a coefficient. And we could come here and say label equals true. Oh, look, they labeled the lines for us. Isn't that great? First of all, they gave it a number label, not a name. Second of all, they gave it number 1, 2, 3, 4, 5. They didn't do us any favors. So fortunately, the coefplot package has another function called coefpath. All you need to do is give it the model value 2. Coefpath. coefplot. When you run that, you get an interactive version of the plot with the proper labels. And you can see that as you increase lambdas, the coefficients are shrinking down to 0, sometimes all the way to 0. I'll blow this up. Isn't this much better? I love this plot. Cool? Why are you not more impressed by this? This is like the greatest thing to happen to glmnet since it was written. That's hyperbolic. But I like this one a lot. OK. With the 13 minutes we have left, if I go, we start a little bit late. If I go a little bit into your lunch break, will you be upset with me? No? All right, cool. I'll try not to go too far into lunch break. Yeah. I love it. Love it. All right. So we see we have a bunch of different lambdas. And what's really nice about glmnet is that it can interpolate between the lambdas. Let's say at a lambda of like 17, a lambda of 15. You just tell, hey, show me the results for 16, and it can interpolate between them. It's a really an amazing equation here. That's part of the reason why it's so fast. So we have these 100 different lambdas, each giving us a very different set of coefficients. What's the natural question to ask? Which lambda? Right? Now, I don't like to say which lambda is right. I like to say which lambda is optimal. OK, so how do we find out the optimal lambda?
There's some figure of merit that isn't.
Some figure of merit. Someone said R squared. What'd you say? Oh, an elbow point. Now, yeah, we can look for that. Actually, I don't even see the elbow point here. So R squared, I don't like to use R squared, because that actually leads to overfitting. Right? R squared, the more variables you put in, the higher your R squared will get. And now you're overfitting. So let's avoid that. Let's throw that out. Louder. Cross-validation. That's some metric of how good the model is. So we could use AIC, we could use BIC, but those are flawed in their own rights. They have their purposes, but they're flawed. Cross-validation has become the gold standard for model validation. So let's go ahead and do it. Thumbs up, thumbs down, do you know cross-validation? OK. Very quickly then, because we don't have a lot of time. If you had, let's say you had a training set and you had a test set, you fit your model on the training set, and you see how well you did on the test set. Right? Well, this is a way of doing you're taking all of your data and splitting it up into 5 folds. In fact, we have a visualization for this. No one needs to do this. In fact, you probably don't have the package installed. Let's do 10-fold cross-validation. There it goes. So basically, you split your data up into 10 discrete sets. And you make your training set 9 of those folds, and you use the holdout set, the temp set, as your validation, as your test set. And then you cycle your way through. You shift it along until every data point has been in the training set 9 times and the testing set 1 time. And then you could take this 10 errors, sets of losses, and average them together to get a sense of how good your model is. That is cross-validation. Cool? Don't worry. If I had more time, I'd go over this in more detail, but we don't have more time, so let's just get right into the code. So we need to build cross-validation now to choose the best lambda. How should we go about doing this? Predict? Well, if we predict right now, we'll be predicting on the whole set. We need to actually break the data into folds. We need to train a model on 4 folds, predict on the 5th. Train a model on different 4, predict on the different 5th. Do it again and again. We need to build a loop. We need to build all this crap. Or
And you've described how finitely, therefore somebody's already coded it.
someone's already coded it.
I think the carrot package has this functionality.
The carrot package does. And the carrot package is awesome. But we don't need to use that. We're going to create a new object called value3 gets cv.glmnet. It's built into glmnet. Does anyone want to guess what CV stands for? Cross-validation, right? So we're going to start off much the same way. X equals land x underscore train. Y equals land y underscore train, comma. Family equals Gaussian, comma. N folds equals 5. That's the only extra new argument we need. OK? That's all we need now. And it will take care of all the cross-validation stuff for us. If we run this, it takes a little bit longer to run because now we're fitting the 100 models 5 times, technically 6 times. But it doesn't take that much longer to run. It is an incredibly fast algorithm. And you did say Carrot, and I love Carrot. In fact, my company, we just put on a workshop with Max Kuhn, the guy who wrote Carrot, literally last week. And it is amazing. But here today, we're going to learn glmnet. All right. Actually, I've done this training here at ODSC a few times. So Max said it in my class one time. So someone was, what about Carrot? I'm like, yeah, Carrot. You know, it's a good package that they stare at Max. And eventually, he broke character and admitted he was in the room. Yeah. All right. Value 3. We fit the model. What happens when we plot this? Let's just do plot of value 3. We get a different plot. R knows that the other model we fit was glmnet. This is a cv.glmnet. And we could get that other plot, which we'll see in a second. But it's showing us a different plot now. On the x-axis is log of lambda. Smaller lambda, bigger lambda. On the y-axis is the error. In our case, it is the cross-validated mean squared error. There are other errors you can use, but mean squared error is the default for numeric output variables. Do you want more error or less error? Right. On the y-axis, the top of the x-axis, you can see for a given value of lambda, how many values were chosen. Let me zoom in on this. Each one represents a different lambda. The dot represents the mean cross-validated error, and the wings represent the confidence interval. Because you fit 5 folds, you now have 5 measurements. If you did 10 folds, you would have 10 measurements, and you can get a confidence interval. This line right here represents the value of lambda that results in the absolute least error. It is the minimum error. It is the best your model can do. That's what you want, the least error. The model, the cross-validated smallest error, is the best fit model. No need for AIC, no need for BIC. Normally, I get a question right now. What's this line?
Yeah.
So this is, well, there's some people who say that, hey, the minimum error might not be ideal. Because the minimum error, we have about, what, 28 variables that are in the model. So they say you should go for the model whose error, while larger than the minimum error, is within one confidence interval of the minimum. So if you were to take the minimum, come to the top of this confidence interval, and draw a line straight across, if I could do it with a ruler, this point here is the value of lambda whose resulting error is the largest you can get while still being within one confidence interval, the best error. And if 2 points are in the same confidence interval, it means they're just about the same.
Some people say that.
Yes.
Some people.
Some people. Some people agree to this statement. Other people don't. Other people are like, modern machine learning, like, what's a confidence interval? Right? But they are incredibly useful. So what we're saying is this model, which has a worse error but roughly the same error, only has 12 variables in it. Let's go with the simpler model because simpler is better. Usually simpler is better. Is that Occam's razor? Right? And just generally in statistics, you're less likely to overfit. Scoring real-time predictions will be faster, et cetera, by going for the simpler model. If we call coefpath on this, coef path of value 3. Similar to before, except it draws in those minimum lines for us, because we've now done cross-validation. And now, if we wanted to, we could do coefplot of value 3, sort equals magnitude, helps if you spell it correctly, comma, lambda equals. Remember, we have 100 lambdas. I need to tell coefplot, it has the default value, but I want to tell coefplot which one we want. There are two ways you can do this when you use a cross-validated glmnet. You could put in a numeric value for lambda, like 0.789, and it will work. Or you could pass it in as a quote, lambda.1se. Lambda.1se will give us the coefficients from the model where that was the slightly worse one. If you had done lambda.min, you would get the coefficients from the model at the absolute minimum. And I forgot to close my parenthesis. And look at that. We now get a much smaller coefficient plot than we did before. Fewer variables were selected because we did variable selection, and the ones that were selected have been shrunk, so they'll be more pulled towards 0. And remember before I said we're not doing a prior, but a lasso can be interpreted as a Laplace prior. So. And Bayes, we're talking about Bayesian stuff, he's buried not too far from here. He's in the city. There's a cemetery there, and you can find his tombstone. It's pretty cool. It's not his tombstone. This is like, it's more than a tombstone. It's monument. Yeah. So, but notice there's no confidence intervals on our coefficients. glmnet, like most machine learning algorithms, don't give confidence intervals. That's a problem, and people are actually researching this. And someone, I believe working with Tib Shirani, developed a method for coming up with confidence intervals. The problem is developing those confidence intervals takes more computational power than fitting the model itself. So they're working on it, but they're not there yet. All right. If you bear with me, I might be able to get you out of here within 5 minutes. How's that? Everyone good? Do we have any questions before I continue forward? You first, then you. All right. So how do you do the n folds? How do you decide the folds? So first of all, we probably should have set a random seed for reproducibility, but we didn't. Second of all, if you don't specify, it will just randomly assign the rows. But you could have your own sampling scheme where you either pre-specify which fold you want each row to be in. You could do stratified sampling to get the rows better. And there's different packages. There's a new R sample package written by Max Kuhn, who wrote Carrot. And that will help you come up with your folds on your own if you want to provide your own folds. Otherwise, they'll just randomly assign rows to different folds. I saw another hand.
Do you need to rescale the x variables?
Do you need to rescale the x variables to use glmnet? So when you're doing penalized regression, the scale of the x variables should matter. Because especially when you're doing that dot product between y and x, that's going to cause a headache. And in order to make sure all the variables are being judged fairly, do you need to scale them? Yes, you do. We didn't. Did we do something wrong? glmnet will automatically scale them for you, do the computations, then put them back onto the original scale. Yeah. Now, if you'd have pre-scaled them yourself, there's an option in glmnet say, don't scale it, I've already done it, but we just let it do the work for us.
This is either going to be trivial or it's going to blow you out of the water. His and mine and yours are a little bit different. Is that just the
You didn't. We didn't set the seed, so it's your shuffling.
It's nothing, yeah.
Yep. Anyone else?
Can you interpret the coefficients?
Absolutely. Can you interpret the coefficients? So glmnet is a linear model, so it's still interpretable. In fact, Hastings Chip had this nice graph. It's like the capacity of the model versus the interpretability of the model. And glmnet falls somewhere like in the middle of both axes. It's still very interpretable like a linear model. And it's almost as flexible. It's not as flexible as trees, but it's still a flexible model. And so now they're the same as the coefficients that come out of a linear model. So there are multipliers. If you had put in a squared term, you could treat it like a squared term. This is perfectly interpretable. That's the beauty of this. Unlike, say, what we're going to learn after lunch, a boosted tree, which is like, well, good luck, right? That's why I love glmnet. Automated variable selection, and it's interpretable. What more do I want in life?
Yes. If your independent variables, sorry.
Outcome.
If your parameters.
Input, you're right, inputs.
Yes, if your inputs are strongly dependent, but those dependencies are often very non-linear, does this mean this is giving you kind of some of the advantages of a non-linear model? But
So you're saying you're saying if your input variables have a nonlinear relationship with the y variable?
no. If the input variables actually have a lot of strong interdependencies.
Oh, with each other.
They are non-linear.
Okay.
These interdependencies are very non-linear.
So the interdependencies between the input variables.
Yeah.
So this is meant to break those. So for instance, if you have two highly correlated variables, regardless of how they're correlated, one will disappear, one will stay.
Yeah.
If you have 5 correlated variables, one will stay, the other 4 will disappear.
Right.
So it's meant to break away from those. You're not getting any of the nonlinearity in there. It's like saying, you know what, we're getting rid of the correlated variables.
You're getting rid of the correlated variables, but not the dependent.
You're right. It deals with correlation, not necessarily dependence.
Right. So okay.
Yeah, it's based on correlation. Well, sort of. A little more detail than that, yeah.
So when you put your input variables,
Mm-hmm.
you no need to log them or square them.
So he's asking, should you do some feature engineering before you do this? You still should, right? You should square them and throw that into another variable, and it will decide if the square is necessary. That's the beautiful thing. So do all of your feature engineering. Put the engineered variable in and put the original variable in, and let glmnet decide. Yeah. Now, some people, they'll square all their variables. I'm like, don't square all of them. You know, use some of your own intuition here. Some will like create all the interactions. I'm like, don't interact all of them. You could theoretically create an interaction between all of your variables, throw them all in, and let glmnet decide what's important. But at some point, it's just going to work on predictive power, not interpretive power at that point. So you still need to feature engineer.
How does this scale the number of variables, cost and memory-wise? Because that was taking an eye blink.
Right. He asked, how does it scale? glmnet is designed for scale. It was actually designed for the use case where he had many more variables than he had rows. It was meant for genomics. And I don't want to say, I don't want to claim it's a linear scaling in the number of variables, but it scales incredibly well. I read the paper 10 years ago how it scales, and it scales remarkably. It's meant for large data. And it's meant for many, many columns. It's absolutely designed for that.
In
And
this context, you cannot test for endogeneity and fix endogeneity problems like with ID or something.
I don't think, well, its real thing is that if anything's like related, it just breaks. It's like, go away. So it makes them go away. Yeah. Something about that, people are asking about that. Oh, yeah. We've only been talking about the lasso. We also have the ridge. We've been doing the lasso so far. If you wanted to do ridge, I'll show you it'll be one little difference in the code. It won't be anything different. Lasso is really good for variable selection. Ridge is really good for dealing with highly correlated variables. If you want to get rid of variables, use lasso. You want to deal with correlation more, use ridge. So if you want to use ridge, I'm going to do a little bit of copy and paste just to make sure things go along here. I'm going to take value 3. I'm going to change it to value 4. I'm going to add one more argument. Alpha equals 0. By default, alpha is equal to 1, which means lasso. If you set alpha to 0, it becomes ridge. If you visualize value 4, we get a different shape. You can see the geometry is different. With the lasso, the variables dove towards 0 and got zeroed out. For ridge, the variables asymptotically go towards 0 but never fully get there. In fact, if we were to do a coefplot of value 4, sort equals magnitude, and lambda equals lambda dot 1se. All the variables are still in the model. No variable selection is performed. It performed shrinkage, but it didn't do variable selection. Now, you might be fairly asking, well, how do I decide if I want lasso or if I want ridge? Right? That's a completely fair question. So the answer is you don't necessarily need to decide. I'm going to copy and paste value 4 just for the sake of time, and I'll call it value 5. And alpha, instead of 0, I'll make it 0.7 or 0.6. And when I do that, it's doing 60% lasso, 40% ridge. And this is called the elastic net. And if we were to look at the coef path of value 5, it should look a little in between the two of them. Somewhat goes a little asymptotic, somewhat dives towards 0. And you get a little bit of a combination. It does shrinkage, it deals a little more of the correlation, and it does a variable selection as well.
So this lasso 60%.
Yeah.
So the obvious next question is,
How do you choose alpha?
yeah,
So unfortunately, glmnet does not have alpha built into the cross-validation. So you either have to build your own cross-validation, or at that point, use caret. And in my book, I show you how to build the cross-validation for alpha nice and easily in parallel. Yeah. So everyone should go get a copy of this. Your bookstores today. And everything you've seen today, it has been covered in the book too. So if you want to read it instead of hearing me, it's there. And I have a lot of videos online going over the same topic. I've given slideshow versions of a talk about this. So there's lots of places to hear me go on and on about glmnet, because I love that algorithm. How's everyone doing? Can I show you one more thing, then we'll go to lunch? OK. Everyone good? I can feel it's a little bit like everyone's ready to be done. Last thing. Let's read in land underscore test. Gets read RDS data / Manhattan underscore test.rds. This is 4,000 rows of data we have not modeled on. All right? So I want to get predictions. I want to take the input values, the input x's, and predict what the output y should have been. To do this, we first need to build up our x matrix again. Now, in order to do this, you need to make sure you have the same data, the same levels of the factors, all of that stuff. I've given you a data set that's already appropriate for this, so we don't have to worry. And we're going to say land x underscore test gets build.x, value formula, data equals land underscore test, contrast equals false, sparse equals true. Just like before, don't drop the baselines and make it a sparse matrix. So let's create a new object to hold this. We will call it value predictions 5, because we're going to use the 5th model. Just like with any modeling function in R, the way you make predictions is with predict. How easy is this going to be? Now, let's do a little bit more terminology. In statistics, we call it predictions. You might call it scoring. But the worst offender is calling it inference. That's what deep learning calls it. They call it inference. The problem is, in statistics, inference means understanding and explaining. And prediction is the complete opposite of that. So really, I'm all for new terms if it makes sense. But when you reuse old terms, that just sows confusion. So I actually gave a talk. It's available on my website. I gave it at this year's R meetup, comparing like machine learning versus deep learning. And the first 5 to 10 minutes was comparing terminology. So you want to learn all the different confusing terminology, check it out on gerrylander.com. Because just all you need to do is get the terminology right, and life gets easier. Anyway, let's predict. We're going to give it the model, value 5. Remember, we have a linear model. All we're really doing is a matrix multiplication here. New x. Most things in R will call it new data. They call it new x, which is kind of frustrating. New x equals land x test. And s equals, in quotes, lambda.1se. I'll put this on the next line. Now, you're like, what the hell is S? Well, they didn't have to build the best interface for this. And when they say S, they mean lambda. Yeah, it goes back to the math in their paper. It actually makes sense mathematically, but not for humans. But you could give it either, just like a coefplot, you can give it a number for a specific value of lambda because it can interpolate. Or say, just give me the lambda that resulted in the 1SE model. And when you do that, and we'll just say head of value predictions 5, and we'll get the first 5 predictions. And theoretically, you could go do mean squared error on your test-wise, but we don't have time for that. And let's say get predictions or scores, or if you need to say it, inference. Don't call it that. Cool. How's everyone doing? Fun stuff, right? All right. So I've only gone 3 minutes into your lunch break. Not as bad as I thought I was going to do. And we started 10 minutes late, so we nailed it. So today we covered a little bit about the formula, but I hope you knew more about that. We learned about building matrices, including sparse matrices and dealing with factor variables. We learned about how a regular linear model could overfit. We learned how to control it using glmnet. We learned how to cross-validate to choose the optimal lambda. And we learned briefly about ridge and the combination of them called the elastic net. And we predicted new data. Whew. If you come back after lunch, we are going to switch to a binary classification. Everyone knows binary classification, right? And we're not going to use a linear model anymore. We're going to use a tree-based model, specifically boosted trees, specifically with xgboost. So have a fun time at lunch. If you come back, I'll see you here at 2 o'clock. That'll be wonderful.